If you have epilepsy, or if you were to, your brain doesn't just randomly decide to have a seizure. There is something before that. Your brain starts changing, shifting, and it's already in trouble. But we find it out when the seizure hits, when it's too late, and that's the actual problem. Treatments exist. Good ones do. Brain stimulation, medication adjustments. They do work, but they all need one thing: time. Just a few minutes of warning could change everything. The gap isn't the treatments, it's the waiting. Over 50 million people live with epilepsy worldwide, and up to 70% of them could be seizure-free with the proper treatment. So, we're going to build an early detection seizure system to buy them that time. First, we need to understand what we're looking for. The brain moves through 3 states. The interictal state, baseline, between seizures, nothing happening. The ictal state, seizure itself, obvious and unmistakable. And the preictal state. The brain is already transitioning towards a seizure, but on the outside, everything looks fine. That preictal state is the hardest to detect, and that is exactly what we're looking for. To build our system, we first need 2 publicly available EEG datasets. One from a sleep center in New Delhi, and 2 from the Bonn University. And now we have to build a pipeline that goes from raw EEG signal to interpretable prediction. First thing we do, clean the signal. Raw EEG is messy. Eye blinks, muscle noise, power line interference, all of it mixed in. We use a technique called PyEMD, combined with time-frequency peak filtering. Why? Split the signal, strip the noise, and then reconstruct the cleaner version. Think of it like separating a chord into individual notes, and then taking out the ones that don't belong. Then, we extract features. Instead of throwing raw waveforms at a model, we pull out 5 clinically meaningful numbers from each signal window: the spike energy and the sharp wave energy, the 2 most recognizable forms of epileptic activity, the energies that a neurological looks for when reading an EEG by hand. Permutation entropy, how complex a signal is. During a seizure, neurons start firing in sync, which makes the signal simpler, so entropy drops. Higuchi fractal dimension, another complexity measure, also drops during seizures. And finally, dynamic feature increments, how much the signal has changed over the consecutive windows of time. Because a seizure isn't an on-off switch, it's a transition, and we want to catch that transition. And now we train. 5 machine learning classifiers, 6 classification tasks across both datasets. We can see that the binary tasks, interictal versus ictal, perform really well. But the 3-class task, comparing preictal versus interictal and ictal, is a harder one. And here's the part that matters the most. Even across different datasets, we still reach around 71% to 73% accuracy rate, which means that the system is not memorizing patterns, it's learning the epileptic brain. But the accuracy alone is not enough for clinical use. A doctor isn't going to act on a black box prediction. They need to know why. So, we use SHAP analysis, a method from the game theory, to break down which features drove each prediction. Spike energy came out on top. Every dataset, every test. That's not shocking. That's what every neurologist looked for too. The system didn't just perform well. It learned the right things for the right reasons. Well, for now the system is done. But there's a ton of things that are waiting to be improved. Like the datasets are small, the preictal tasks need more data, and there's real room to push with deep learning. So, let's continue on working. The warning is there. We just need to learn how to read it, early enough to actually do something about it.